In this video, we're searching for the angles at which a cardioid curve is going to have horizontal and vertical tangent lines. So we'll get a formula for the slope real quick, and we recall the conversion between polar and rectangular coordinates. X is r cosine theta, y is r sine theta. And to change my slope into polar form, all I do is divide the numerator and denominator of dy dx by a d theta. So I need to compute dy d theta over dx d theta. When I take the theta derivative of y, I have to keep in mind that r is a function of theta, so I have to use the product rule in this derivative. And I get r prime of theta sine theta plus r of theta cosine theta, similar in the denominator. And there's our quick derivation of the slope formula in polar coordinates. Now I need to plug in my curve, and before I do that, we'll just note really quick here that r prime of theta is equal to 2 cosine theta. And so I plug it in, and I plug r in to the second term here. Same thing in the denominator. And I can clean things up a little bit before I get into finding my tangents. In the numerator, I have a 2 cosine times sine, and then when I distribute the cosine over the second term, I have another 2 sine times cosine. So I'm going to write down 4 sine theta cosine theta. The other term I get when I distribute the cosine is a 2 cosine theta. In the denominator, I have a 2 cosine squared theta. And then when I distribute the sine theta over the 2 plus 2 sine theta, I get minus 2 sine squared theta. And the last term is a negative 2 sine theta. So to find horizontal tangent lines, we're looking for where the numerator of this thing vanishes. And I can divide a 2 out of this equation. And I get 2 sine theta cosine theta plus cosine theta equals 0. And our goal here is to find the thetas where we have horizontal tangent lines. Well, I can factor out a cosine. And I get cosine theta times the quantity 2 sine theta plus 1 is all equal to 0. This equation is solved if either one of these factors is equal to 0. So I can have cosine theta equal to 0, and I'll have a solution. Or I can have 2 sine theta plus 1 is equal to 0, and I'll have a solution. So where's the cosine of theta equal to 0 if I'm graphing this thing on 0 to 2 pi? That happens when theta is pi over 2 or 3 pi over 2. What about 2 sine theta plus 1 equals 0? Well, that's the same as saying the sine of theta is negative 1/2. And this occurs at theta equals 7 pi over 6. And theta equals 11 pi over 6. Again, we're assuming we plotted this thing on the interval 0 to 2 pi. So if we start to look at these things, at theta equals pi over 2, that looks pretty good. It looks like there's going to be a horizontal tangent right at the top of the cardioid. But then when we look at theta equals 3 pi over 2, that's when we're aiming straight down. It looks like that's the angle that gives me the cusp at the origin. If I do the calculation real quick, r of 3 pi over 2 is going to be 2 plus 2 sine 3 pi over 2. And sine of 3 pi over 2 is negative 1, so this is 2 minus 2, and it's 0. So we are indeed looking at the origin, and there's a cusp there, which means the slope of the tangent line shouldn't be defined. How can we find this algebraically? If we look in the denominator, if I evaluate that at 3 pi over 2, the cosine term vanishes. And then I end up with a negative 2 sine squared of 3 pi over 2, which is 1, minus 2 times the sine of 3 pi over 2, which is negative 1. And that's negative 2 plus 2, and that's 0. So theta equals 3 pi over 2 corresponds to the numerator vanishing, but also the denominator vanishing. And I end up with a cusp there. And the slope isn't defined, and so we're going to throw that one out. The last two are more straightforward. 7 pi over 6 looks like a horizontal tangent. And 11 pi over 6, that's pi over 6 less than 2 pi. That looks good too. Okay, what about our vertical tangents? So vertical tangents will occur when the denominator of the slope function vanishes, but the numerator does not vanish. We already know the denominator is going to vanish when theta is 3 pi over 2. And that corresponds to that cusp, so we got to throw that one away. And I'm trying to solve the equation 2 cosine squared theta minus 2 sine squared theta minus 2 sine theta is equal to 0. And I'm going to divide a 2 out of this to begin with. And so I have this quadratic equation, but it has a squared cosine and a squared sine in it. And if I could just change everything to sines, I might be able to factor this quadratic equation and solve it. So I'm going to replace cosine squared with 1 minus sine squared. Now I'm going to combine my sine squared functions, and I'm going to multiply everything by negative 1 to clean it up. So I had a negative 2 sine squared theta, that's now a 2 sine squared theta. I had a negative sine, that's now a positive sine. theta. And I had a 1, and that's now a negative 1. That's all equal to 0. So this looks just like a standard factorable quadratic equation, like 2x squared plus x minus 1. It's just that our variable thing is sine theta. So I'm going to factor this. And I know if it's factorable that it would factor into two binomials. One of them starts with 2 sine theta. The other one starts with sine theta. And then it's just a matter of guessing the constants correctly. And I want to get a positive cross term here. I'm going to put the plus 1 right there. That gives me a plus 2 sine theta. And a minus 1 right here. That gives me a minus sine theta for the cross terms. And the negative 1 checks out for the constant. Now this equation is solved if either one of those factors is equal to 0. So if 2 sine theta minus 1 is equal to 0, we have a solution. That means sine theta is 1/2, and that occurs when theta is equal to pi over 6. Or when theta is equal to 5 pi over 6. The other solution we get is when sine theta plus 1 is equal to 0, which means sine theta equals negative 1, which means we're talking about 3 pi over 2. And that's that extraneous solution corresponding to the cusp, so we have to throw that out. Then when I go to the graph and look at theta equals pi over 6, that's right here. That looks pretty good for being a vertical tangent. And finally, I look at theta equals 5 pi over 6 right here. And there's our last vertical tangent line. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.